Hello, everyone, professor and classmate. I hope you're all doing very well and having an excellent day. My name is David Felipe Garcia Lozano, um, and today I'm going to talk about a very interesting scientific article titled The Quantum Relativistic Harmonic Oscillator, a spectrum of series of its wave functions. Writing by Sarso and Martinez in 1993. This research combines three fascinating fields: quantum mechanics, relativity, and mathematical physics. Let's continue with the first question: what the article is about. The article focuses on the relativistic version of the quantum harmonic oscillator, one of the most important models in physics because it helps explain vibrations and oscillation in atoms, molecules, and even electromagnetic waves. In a simple quantum harmonic oscillator, we study how a particle moves back and forth under and restoring force like a spring, and how its energy is quantified. But in this paper, the authors take it one step further by including relativistic effects, meaning they analyze what happens when the particle moves and at a speed close to the speed of light. To describe this, they use mathematical functions called relativistic Hermite polynomials or RHP. These are a relativistic version of the classical Hermite polynomials which are used in the non-relativistic case. This general relation allows science to understand the behavior of quantum systems that operate in high energy conditions where both and quantum and relativistic effects are significant. Let's continue with how the article is relation with the physics of waves. Now, how does this topic relate to the physics of waves? In quantum mechanics, particles also behave like wave. Particles behave like waves described by a mathematical function called a wave function. The wave function oscillates in space and determines where particles are most likely to be found. The author studied the series of this wave function, the exact point where the waves cross the horizontal axis and the amplitude is zero. Interestingly, the distribution of this series tell us important physical information. When the zeros are close together, the waves oscillate faster, which means the particle has higher kinetic energy. When the zeros are more spread out, the energy is lower. This direct relationship between the spacing of zero and the particle energy beautifully connects mathematical structures with the behavior of waves in quantum systems. It also helps visualize how waves change under relativistic conditions. And for finish the question, how the study was developed. To analyze all of this, Sarson and Martinez used a mathematical technique called the WKB approximation, which stands for Wenzel-Kramers-Brignoni. This is a semi-classical method that gives approximate solution to the Watt equation when the system is too complex for exact answers. With the WKB approach, they obtain an analytic expression for how the zeros of the relativistic wave function are distributed. Then, using potential theory, they prove that this approximation matches the correct asymptotic distribution, which means it becomes exact when the quantum number gets very large. Finally, they demonstrate that in the non-relativistic limit, the results reduce to the classical case of the normal quantum harmonic oscillator. For conclusion, to sum up, this article builds a bridge between quantum mechanics, relativity, and the physics of the waves. It showed that by studying the zeros of the relativistic wave functions, we can understand how energy and oscillation patterns behave in systems moving near the speed of light. This study not only depends on understanding of the behavior of waves in extreme conditions, but also highlights how mathematics can reveal the hidden structure of physical reality. Um, Thank you very much for your attention, professor and classmate. I hope you found this topic fascinating as I did, and I really appreciate to the opportunity to share it with you today. Thank you for watching.